Right, let's continue. This is question 2a. We're asked to find the DTFS of these two pure sinusoids added together. One is at omega pi over 3 and the other one is pi over 4, a sine wave. Now please compare later on with question 2ai, where it was a cosine at pi over 4. Now it's a sine at pi over 4. Since there are two sinusoids of different frequency, and we're asked to find the DTFS, the first thing you need to do is to find the capital N, the period of these two sinusoids. Let's do it one by one. At pi over 3, we use the same approach, small n plus big N is equals to this expression on the right, and we are basically trying to find N to be some integer numbers such that it will make this expression on the right to be the same. We found that N is equals to 6. And in this particular example, the K here, the number of period is K equals to 1. For sine wave, now, please think, pi over 3 or pi over 4, who is rotating faster? Pi over 3 is rotating at 180 divided by 3, which is at 60 degrees per sample. Pi over 4, it is rotating at, let's say, pi is 180 and 4, and therefore we get 45 degrees. So definitely this cosine is rotating faster than this sine. Alright, that's how you start to imagine discrete time sequence, digital angular frequency, and what it means. Now, if we carry on, what we will realize is that this sinusoid will repeat every 8 samples. That's what we got the previous time as well. So that's the problem. On the top, we're rotating as we are being periodic at 6 samples, and in the bottom is 8 samples. So the lowest common multiple of these two sinusoids would be the fundamental frequency of this sum. How should you think about it? Well, you should think like the cosine is repeating at 6 samples, 12 samples, 18 samples, 24 samples, and so on. While at the bottom, for 8, we are repeating 8, 16, and 24. And you realize that both of them will repeat at 24 samples as well. So the common period between these two sinusoids is 24. That's what we are talking about in this lower common multiple. So what we are basically going to do is that we are going to divide this omega from 0 to 2 pi somewhere on the right hand side, and each step we are going to break 2 pi over 24. So this is pi over 12. So at every interval along the horizontal axis of the DTFS, we're breaking it to by pi over 12. So the second one is 2 pi over 12, and the third one is 3 pi over 12, and until the last one, of course, is we are going to be at 2 pi. That's the idea. So the omega naught is a digital angular frequency, and this is the capital N that we are interested in, the period of this common sinusoid. Now, we then want to express cosine using complex exponential as before, and of course we immediately apply the Euler's equation. But this is not enough. We want to express this with respect to omega naught. Okay, so we know that this is going to be pi over 3n plus e minus j pi over 3n, the positive and negative frequency. But the key idea is that we are going to express this in terms of this k times omega naught. So omega naught is fixed, pi over 12. So 4 times pi over 12 becomes pi over 3. So this is okay by choosing little k equals to 4. And here by choosing k equals to minus 4. So that's the minus sign here. Okay, that's the idea for cosine. And now, therefore, we now can say C4 is equals to this value half here, which is here, and C minus 4 is also half here. Alright, later on you will see that because it is 2 pi periodic, or at least in this example is 24 samples periodic, then C minus 4 is the same as 24 minus 4, C20. Okay, and for the sine, well, again, we are going to express it with respect to omega naught, and omega naught, as you remember, is pi over 12. And since it's pi over 4 is equals to pi over 12 times 3, that's for positive frequency. So now we know k equals to 3 here, and k equals to minus 3 here. So we again find C3. Now, the difference between the cosine and sine is that the complex exponential subtract, and we divide by 2j. So the coefficients at the positive frequency is 1 over 2j, and the other guy is minus 1 over 2j. So this is C3, and this is C minus 3. Okay, so go and work out your complex numbers. We are not interested in 1 over 2j. That's a number we don't like. So to form a complex exponential representation, the simplest way is multiply top and bottom by j first. Then it will be j over j squared. J squared is minus, so minus goes in front. But what is half? So this number is actually 0 minus 0.5j. Okay, so this number, the magnitude is 0.5, and the phase is minus 90 degrees. So it's minus pi over 2 over here. So C3 is this expression, and C minus 3, later you can work it out, is the magnitude is here, and the phase is actually the conjugate of C3. This is plus j pi over 2. Right, with that, then now you can sketch the magnitude and the phase. So this is the magnitude of the sinusoid at k equals to 3. This is at k equals to 4. All the magnitude is the same. Okay, so I should draw it here. The magnitude is half, and for this guy, the magnitude is also half. But for the sinusoid, at k equals to 3, the phase is minus pi over 2. At c at minus 3, the phase is at plus pi over 2. So this is the DTFS representation that we have just worked out. So sorry about this. This is the DTFT representation. So what we'll do for the DTFS to the DTFT is two things. We would first multiply the magnitude by 2 pi, and then we will convert the k representation into directly omega, and it is very simple. We just take the k index by omega naught, and omega naught is 2 pi over, in our example, it is 24, or it should be pi over 12. Multiply by k from 0 to 12, or from k equals to 0 to minus 12. With that, I think we have just done the DTFS and DTFT representation of this complex exponential, summing this or representing this sinusoid as complex exponential. Some remarks. This is the double-sided spectra. Okay, this is a double-sided spectra. If we want to do the single-sided spectra, then we will do from 0 all the way to 24. Thank you.